club where ordinary parents encourage one another to develop an extraordinary appreciation of math. We love what we know and struggle over the unfamiliar. Through weekly conversation and exploration among friends, we can begin to enjoy ideas that seem difficult. Join our book club as we discover how math helps us to know God and to make Him known.
Hi, and welcome everybody to the Math Map Book Club. It is Wednesday, October the 2nd, and we are here working through the Math Map, the complex domain, which is CC's new math curriculum that is guiding parents to seek out God by seeing the unseen, and guided through the classical method, and joining the math conversation. So developing community at home and in community with one another. So thank you for being here. We are moving on to lesson 10, which is about intersected lines. And so it's exciting to be in the second dimension. And I don't know if we mentioned this last week, but I often think that the second dimension feels like where a lot of what we think of as high school math takes place. And so when we experience math linearly, a lot of the times we think of that first D, that arithmetic, as being what we do in our primary schools. And then in our secondary schools, we start looking at algebra and geometry, which feels more like what we're doing in 2D. And I want to just encourage us all to kind of break that paradigm down and understand that we're doing, right, we're looking at all of this in a classical method. And so the first time going through, we're really looking at the grammar of all of these topics. And so for a lot of our students, these 2D topics may be really unfamiliar. And as parents, we may feel that they're more familiar to us because we've seen it before. And so I really want to encourage us all to, as parents, enjoy being dialectic because we're seeing something for the second time, wrestle with those ideas, but let your kids rest in the grammar, and let them encounter new things. And they may have some, why does this work, right? And I'm not saying don't ask, right? But don't try to force them to understand everything this first year through. Really, there's a lot of rest in that grammar phase of learning where we're accumulating all of this language about math. And we're going to see it again next year and the year after that. So I just want to encourage us all not to be rushing ahead. So as we start every week, we are looking at our math map. And so we are here, intersected lines. So I like to highlight that so we all know where we're going to be this week. And then wherever you are, so if you want to look at your cover, identify your domain and your color, that is on the left-hand side. So if you, hopefully by now you're realizing where you're at, but if you need that, that is where we find it. And what I am using is this complex. And so where those two meet is where we're at. So we're going to change up our N2K a little bit this week. So we're trying out a new idea here, and we're going to call this the domain game, but we're using N2K rules. And the idea is that we can still come up with three numbers. We can use our dice to come up with three numbers. And our quote unquote function is going to be using the N2K rules, right? And so notice this isn't really a true function in the terms of something that we would write arithmetically or algebraically. But we're just going to say that your function, your way of mapping from your domain to your range is to use your N2K rules. And so you're limited to just the numbers 5, 1, and 2, but you can use your N2K rules to develop your range. So just a different way of looking at N2K, but making it so that we can help students to understand when we talk about domain, these are the numbers that I can use and the range are the numbers that I'm generating. So it's a very broad understanding of domain and range, broad understanding of function. So we're just going to try it out today. So I'm going to get our timer started, and then you can go ahead and tell me. You can just say your numbers, and I will write them in the range.
So could we do something like 5 cubed is 125, times 2 is 250, times 1 is 250?
Yes.
Okay.
Remember, 5 plus 1 is 6 plus 2 is 8.
Can I do 5 to the power 0 is 1 times 1 to the power 0 is 1 times 2 to the power 0 is 1, so it's 1.
I'm too scared to say something. I know it. I'll say it.
5 times 2 plus 1 is 11.
I was gonna say that. No, we do. Goodness, 5 squared is 25, plus 1 plus 2 is 28.
5 times 1 is 5, plus 2 is 7.
5 squared is 25, plus 2 is 27, times 1 is 27, minus 1 is 26.
Five squared is 25, plus 2 cubed, which is 8, plus 1 is 34.
Minus 1 is 33.
5 times 2 minus 1 is 9.
Or is he? He did it. He did it. Okay, good for him.
2 cubed, 2 to the third power is 8, times 5 is 40, times 1 is 40, plus 1 is 41, minus 1 is 39.
All right, great. So what did you guys think? Is that a fun way to change this game for students?
Yeah, it's a nice switch up.
And you could do, so maybe nobody else plays these mind games like I do, but one of the things that I've really enjoyed doing over the years is always like seeing if you take football scores, right, your possible scores, you can get 2 points for a touchback or a safety, right? I mean, 2 points for a safety, 3 points for a field goal, and 7 points, 6 points for a touchdown, and then 1 point for your extra kick. Although that one's kind of, it has to go with the 6. So it's either, anyway, and then 2 points for your 2-point conversion. So if you have boys and they like football, giving them those numbers and then say, okay, see how far you can count up, right? So there's a lot of different ways you could take this, right? And say, okay, could you count from 2 to, 49, right? Are all of those scores possible in a football game? It sort of takes the same kind of idea, right? Where you could pick random numbers, but if you have sports fans, right, boys, that might be a way to encourage them to play a little bit differently. So anyway, so just some different thoughts that there, if you're looking to change up your N2K a little bit, whether that's at home or in community, this is just one idea that we thought we'd try today. So
I have a question though, Dr. Gilpin.
yes.
Because the function is range, so isn't it theoretically you could do a power 5 to the power of n and you can go up indefinitely?
You could, yes.
Okay.
So if you have kids in your, so we're going to be releasing in the spring, we're going to be releasing the exponents and then roots and logs as flashcards. And so we're going to be really encouraging, right, that remembering those powers. So that's another, right? So if you were looking to practice those, this would be a way to bring some of that practice in and extend it beyond maybe just what we have, here. So yeah, you could go as big as you want. And that might be something else. So if you have kids that are like, I'm done with this, or I've done that, and you want to encourage them, they could get really big numbers, but you could also go really small numbers, right? So notice that we all thought about natural numbers here, but you could have put, you could have maybe have decided to put negatives in,
Yeah.
right? You could have made one of your numbers negative, or you could use negative exponents. So I could say, right, the 1/2 power of, or the negative, sorry, not the 1/2 power. You could use that, but let's say the negative 2 power of 5. Well, now that's 1/25. And so there you could now incorporate practicing fractions, right? Say I told my kids they had to use the -1 power and addition for all of these. You could practice 1/5 plus 1 plus 1/2. So just some different ideas, just some different ways that you could take that same kind of idea, but switch it up to bring that practice, that computation practice in if you wanted to.
Yeah. Thank you.
You're welcome. All right, so let's go ahead and take a look here. We have a piece of art by Rembrandt. And we're going to come back to that because I first wanted to read our quote here by Aristotle that says that at the intersection where your gifts, talents, and abilities meet a human need, therein you will discover your purpose. What do you guys think about that? Especially, right, taking this idea of intersection, but now what can that teach us maybe about our spiritual lives?
This reminded me of my daughter who's starting nursing school soon. She was debating whether or not she should postpone starting, and she encountered a medical situation. And she's like, God showed me my purpose. I needed to help that woman. I was fully in control. I had the ability to help her. So this reminds me of just how God worked all those things together. And she is starting nursing school in January. So
Well, that's beautiful.
Jesus is the intersection between like our horizontal relationship with people and our vertical relationship with God.
That's great. And that's important. Isn't that so important to remember that that we have this vertical relationship with God that matters, but we also have this horizontal relationship with people, and first within the body, right? That we minister to one another in the body. And so we think of that idea of gifts and talents within the church, but then also that he's using us outside of the body, right, to draw others to him. So that's beautiful.
Also, that the intersection is not always 90 degrees, that it varies.
It's a great point.
And also the cross itself representing horizontal vertical relationship too.
Yes. So let's go ahead and take those ideas that we're thinking about our gifts and talents that are God-given, right? So we maybe see those coming from that vertical relationship that we know that at the time of our salvation, we're fully equipped for all the good work, right? That he gives us the gifts and the talents and the abilities to then go out and minister in his name. And so how do we see that portrayed here? And so Kylie was right pulling the cross into that. What else do you see in this piece of art?
Light and darkness.
Where else have we thought about light and darkness?
in division.
Does the cross divide anything?
It can divide us from our sin.
Yeah.
It can divide us from all other loyalties.
Yes.
But it can also connect us to the Father, right? He's the bridge.
I was going to say that it separated Jesus from his Father.
Yes. When Jesus himself talked about his purpose, right? When Jesus himself came in and talked about right, why he was here, he said that he came to separate, right? And that following him and taking up our own cross, right, can separate families. It can separate, right, because it's separating us from the world. But yet in that separation, it's also a bridge. When we think about last week and moving into 2 dimensions, what does that cross maybe remind us of mathematically?
The abscissa and the ordinate.
Great, those 2 axes, right? And so what do those axes do to our plane?
Divides it into quadrants.
Yes, right. So those axes, right, there's a division there. So for somebody who for years and years, right, really did not like division, right? And if you've read the travelogue at all, you'll see some personal testimony of like, I didn't really like division, right? But we see right through the Bible and through our conversation here, how important that division is. Because can we really cross that bridge and be with the Father? Can we be united with one another in the body of Christ if we're not separated or divided out from the world? So God is working to redeem division for me, right? By showing me that sometimes, right, division leads us to some really beautiful things. And so this idea of intersection, right? And the other thing, right, is we always say that God meets us where we're at, right? And so we don't have to get all pretty for him. We don't have to be perfect for him, right? That wherever we are, when we say, okay, Jesus, I'm ready, he'll meet us right there. We don't have to be anything else. So there's another sense of an intersection or a meeting, right? That he comes to us. All right. So let's go ahead and look at our I squared invention page. And so let's just take a minute and have everybody tell us everything you know. So it may not be everything, right? But tell us some things that you know about lines.
This brings back memory from my high school. We're talking about the cosine and tangents and what's the other one? Sine. Lines. Yeah, it kind of it's a fun revisit, but that's all I have to remember. So it's kind of exciting that, oh, we're seeing this. It's familiar, but yet so unfamiliar.
The degree is 180 degrees.
Okay. That's good.
Infinite points.
Infinite points on a line. Good.
It stretches to infinity, both negatively and positively.
Good. Great. So if we were to define some words, let's take a look at the bottom right where we see a word and then a phrase. So I want to talk about the word alternate and the words same side. And you don't necessarily need to think about this mathematically, right? But if you were going to define the word alternate, what would that mean to you?
Flipping and flopping.
To go back and forth.
Back and forth.
Every other.
Every other. Good. So now if I say, it says here that alternate interior angles, and it says 3 and 6. So go ahead and find angles 3 and 6. So here's 3 and here's 6. So how do we take that idea of alternate, of back and forth? What does it maybe tell us about their relative position with respect to this line T?
So the alternate part's the left and rightness compared to the line.
Good. So one's left, one's right, right? So they're on different sides. So we took what we knew about things that alternate and we're just applying it here. So how about same side? What does same side tell you?
The same side of the line.
Yeah, both left or both right.
Yep, there you go. They're either both left or both right. And so here we see, as Lee pointed out, right, 3 and 5, they're both on the same side of the line. So those are some words that we could define and then look at and see if we understand them mathematically. The last thing I really want us to take a look at today is this middle piece, which connects to the top picture here. But this middle piece, it says graphing line notations. And I wanted to point out that these notations for different lines are unique to the math map. And these are not necessarily things that are going to be true in every curriculum or with every mathematician. Now, generally, a dashed line that we use as a dashed line will be a dashed line in another curriculum or with another mathematician. But they could all be the same dashes. Within the math map, Lee has really tried very hard to come up with some different ways of giving you visual hints as to whether the line you're looking at is an asymptote or a limit or the directrix, right? Or the line of reflection. And so that's why these lines are here. Now, there's a lot of lines here that the students haven't seen yet. And so you might look at these and go, I don't know what these mean. But I would just maybe put a bookmark, a little sticky note on this I² page. And as you encounter graphs over the next several weeks, and you want to go back and say, oh, wait a minute, I think, is this a limit or an asymptote? Oh, I can go back and I can look and see which one this matches up to. And so that's the purpose here. Again, the dashed line, anywhere else is just a dashed line, but within the math map, Lee is trying to give students those visual cues to help them determine the job that that dashed line has.
So one of the reasons we did that is, like, for example, if you had a function where you have both a line and it's being reflected in such a way that there's an asymptote, and then you want to be able to talk about it simply visually, it helps the children to have different graphics for each of those words.
Let's go ahead and take a look at our I³ page, our Memoria and arrangement page. And I think this is one of our more classic memory work types of pages. So let's go ahead and take a minute and talk about what are some different approaches that you might take for your own, if you were trying to remember this for yourself, or if you were working on this in your homeschool, what are some approaches you would take to begin memorizing the information on here?
Flashcards.
Yes. And those flashcards are coming.
We could just copy it.
You could copy it, great.
I will compare each other.
Comparing, what would you compare?
I will pick one line is very familiar with. I will start with 0, simple enough. And then go to the next smallest one, a cube, and to see what is the difference.
Good.
You could also start with the ones that are most familiar, like the 0 and then maybe you could draw a highlight line through that, and then maybe 90 degrees, 180, 270, and 360, just to kind of get your bearings, and then kind of see the relationship, like what's in between those.
Good.
So I'm tempted to have my class do a cheer, like with the 0, 90, 100, what's like, or even backwards, like doing it backwards, like you could really like get some arm movement going there.
It's good.
That's great, Carrie. So Carrie, keep that thought in your mind right there. And I want you to look at the degrees and the radians columns. And how could you use the same motions forwards and backwards to do all of those columns?
So you mean like, hold on. Like depending on which direction I'm going with it. So like 0, pi over 4, is that right?
Well, 0
Pi,
matches with 0.
and
Right.
then, wait, hold on. And then 90 is pi over 2.
Yep.
180 is pi. Yeah, that could be a fun chant.
Yeah. And then notice the other ones, you're coming back and you could do the negatives coming backwards.
Yep. Yeah, that's fun.
So you're going to notice, again, pointing out here that these angle measures here are a great set of pegs that if your students, right, maybe not all this year, but they're going to become familiar with these over the course of this year, because we tried most of the time to use these angles to encourage students to become familiar with these. And so we're going to see these angles over and over again, just like we have our functions that we're going to revisit. These are going to be angles that we revisit. And so we're going to see these angles and become familiar with them. So that's one of the reasons why we've got them here, because it's going to help students if they start memorizing this, but even if they don't do that, they're going to become familiar just because we use them so much. All right, let's go ahead and take a look at our charts. And again, these are charts 1 and 2, but if you have yours at home, you can certainly pull from those. And let's go ahead and share some things that are familiar or some things that are unfamiliar.
Well, the intersection of two lines, I'm familiar with the slope, y equals mx plus b.
Good.
I see parallel lines and perpendicular lines. Those are familiar.
In the top box on the right, I see this terminology, terminal side and initial side. I've not heard that before in math, but just like you were saying with alternate and same side, like I can figure that out from my other spheres of life. I know what those words mean.
Good.
Kirsty, you probably should take a stab at explaining radians, because it's on here and people have questions.
Sure. So radian is we are oftentimes most comfortable with 360 degrees, right? And so we measure things in terms of 360 degrees. A radian is used in a lot of mathematics because it is really a ratio. And so it doesn't have any degrees or units. And if you have noticed, right, when Lee puts a lot of units in the math map, right, to make sure that we keep track of those, because a lot of times we're tempted to drop them off. So we're being trained to keep track of those units, but especially when we're working with measures of angles, those units can kind of feel like they get a little bit in the way. And so radians give us a way of operating without units. That's why they're so popular. It also gives us a way, and you may not see this year, but it's going to take because it's a ratio, when we start doing trig, it helps us to have to do our graphs a little bit differently so that we can actually go back and forth between our angle measure and our sine value, our ratios. And that's kind of beyond what you're going to need them for this year, but that's where we're headed. And so what it does is it says, let's take the circle, right? And we know that my circumference of a circle is 2 pi r. And then let's take one radius. And if I was to take that radius with a piece of string and I was to lay it around my circle, right? How far would it go? And I'm going to just draw this on the screen here so that you can picture this a little bit more clearly. I don't believe I said more better almost. So here's my circle. It's going to show up in a minute, right? And so I take my radius, and if I was to lay this radius out on my circle, wherever I get to, if I was to draw the radius to the other end of that, so this is r, this is r, and although it's curved, its length is r, right? So this is 1 radian. And if there's 2 pi r radii in the circumference, how many radians would there be? There's going to be 2 pi, right? So my circumference is 2 pi times r. It tells me there's 2 pi r's. So there's going to be 2 pi radians in 360 degrees.
So if pi is about 3, it tells you there's about 6, because 2 times 3 is 6. 6 of those r's to go around a circle.
So we're going to do more with this. You're going to see a lot more of this in lesson 13. So in 2 weeks' time, we'll talk more about radians. But for now, we're really using this as memory work, right? So one of the reasons why people think radians are hard is because they're unfamiliar. We're just used to talking about things in terms of degrees. And so one of the things that we can do for our students is just build up that memory work of, okay, 90 degrees is pi over 2, right? And if I know that and I start becoming familiar with it, then it's not going to be hard anymore, because they have that mental picture and know that if I'm talking about that vertical, well, that was 90 degrees, but it's also pi over 2, right? I'm going to start having that mental image of where those radians are, and they're going to become familiar, and they're not going to be hard anymore because they're familiar.
So I have a question about that. This morning when we were doing math, my son came to a conclusion and goes, I think in a lot of things in math, I don't understand it. It is just is. It just is. And then my rhetoric mind wants to explain why is it? And I want him to understand the why. But I like what you said about resting it in the grammar stage. But then, so what can I say to a child who asks why a lot and who wants to follow his or her train of thought, even though his brain is not quite developed yet, and try to come to a conclusion that why is pi 3.14? Well, because it's just is, because when we were taught is like, this is r, pi is 3.142, and just memorize it. But to a child that asks why, what do you say to them?
So I would say it, just like with our little kids, right? When they go through that why phase when they're little, is pick and choose, right? Pick and choose the things that you really want to explore this week. And if it's why is pi 3.14, right? Okay, well, let's go and explore that. You might find a couple of videos of people who are showing you, right? Because it's one of those things that can be demonstrated through videos. Or you might say, let's just go and find a whole bunch of circles, and we're going to measure those circles, and we're going to ourselves just go ahead and look at if pi is circumference over diameter. Let's go measure a bunch of circles and divide their circumference by their diameter, right? And we're just going to keep doing this a lot of times and see what we come up with. And that so that for that student, if that's his question, maybe that's what you do, and you just pick one or two things that you decide to go and investigate more, and let them know we may not understand all of the why this year, because sometimes we don't necessarily have the grammar or the vocabulary yet to understand the why. So we need to develop that first, but we can pick some things that we might dive deeper into. So you might look in the companion at the material that's in there that's linked to the charts, and look for something a little bit deeper, or explore yourself, right? Like doing something like that with pi to answer those questions.
Okay, thank you.
Something also I think that helps is to find something they can relate to, like say, why is blue called blue and not yellow? Right. There's some things that are just come out of a common language, and that's the beginning of grammar, is memorizing that common language. But you can also use an analogy here of other words. So instead of saying 180 degrees, I'm looking at the middle of the chart on the left, I could say 180 equal units. So instead of saying pi radians, I could say pi equal units. So 180 degrees, I can picture, most of you probably can. So in order to remember this, I always use a snake. And I say that means there's pi snakes, because a snake can curve around it. Yeah, right? So then, and the snake is an equal unit. It's the same size snake. It goes around that 180 degrees pi times.
Yeah.
So you could have said pi jump ropes or pi something to show that it just is referred. So a radian is just an equal unit, just like degrees, all are equal units. So there's ways to make things fun and the hands-on, like Kirsty suggested, and there's also ways to make it fun where you mess around with words, kind of like Lewis Carroll did, and see if that helps you at all.
I think that would. Thank you very much. I think just to bring it to everyday life and use little people language. Like I love the snake example. He loves snakes, so that's great. Thank you.
The problem is that 0.14 of the snake that you got to cut off the rattler tail.
All right, let's go ahead. And are there any questions from last week where we talked about straight lines? All right, well, let's go ahead and look at a couple of our page tops for this week. And our first page, notice it says, we're going to go ahead and read it. Label clockwise, CW, or counterclockwise, CCW, and the initial and terminal rays. So as Jana pointed out, some of that may be unfamiliar. So we may want to go back and look at the chart to help us figure out what we're doing, or we may want to think through what do those words mean, right? So if initial and terminal are unfamiliar, how do you understand them? Don't think about it in terms of an angle, but what does initial mean, or what does terminal mean?
Like stop and start?
Good.
Beginning.
And
end.
And end, good.
I think of the airport because you initially have to go through all these things and you wind up at the terminal.
Good. So we may have to help our kids with these words to connect them to understanding that's outside of math. So now when we bring that inside of math and we think about an angle, what do you think the initial and terminal sides of an angle are?
So, Kirsty, is it just where you're starting and ending your measurement?
That's all. Yep. So I'm going to start, here's my initial side, and I'm going to rotate, and there's my terminal side. Right. And so when we think about angles being a rotation, we need a place to start and a place to stop. And that's all that we mean by initial and terminal. Now, when we talk about initial and terminal in the plane, not in the coordinate plane, it doesn't really matter which is which, because our measures are going to be positive always. And so it doesn't really matter whether this one's my initial or this one's my initial, but we just want to help students see that an angle has to start, right? That the rotation starts at one place and it comes to another place, and that makes our angle. When we look in the coordinate plane, we're going to see that it's a little bit more specific than that. But for now, we just want to help students understand that we have a starting ray and we have an ending ray, and the angle is the measure between them. So how about clockwise and counterclockwise? What does that mean?
It follows the directions of a hand on a clock, or it doesn't.
Yes. So, right, I have a student, I have a child who loves handed clocks and analog clocks. They think that they make the most sense, like me. And I have a student, a child who says, I really don't like those. I have to think. Just give me a digital clock any day of the week, right? And so depending on your students, this may be something that is really intuitive, and or it may be something that you have to help them really think through. So as we look at this exercise, right, we've given that hint that we've got clockwise, and we're given this hint here that the clock, we're going from 9 around to 3, that's clockwise. If we were to go the other way, if we were to start at 3, right, and time travel back to 9 o'clock, notice we would be going counterclockwise.
Kirsty, I think you misspoke, or we didn't understand your context. You said something about no negative degrees in a certain situation, right?
Right. If we're just in the plane, and if we're not in the coordinate plane, in the coordinate plane, we have positive and negative degrees. If we're not in the coordinate plane, they're always going to be positive degrees.
Girls, it took me 5 years to get that in my head.
It'll take me that long too.
Can you say it again, please?
Sure. So if I'm in the coordinate plane, right? So if I'm in the coordinate plane, I have axes and I have coordinates. We're going to discover that this direction is a positive angle, this direction is a negative angle. But if I just draw an angle in a plane and there's no coordinates, this is always going to be positive. It doesn't matter if I go that way or this way, it's always going to be a positive measure.
It's kind of like distance. Like if you walk from here to anywhere, you're always going in a positive, doesn't matter. But if you put it on a number line, for instance, and you walk to the left, it's going to be negative.
Yes.
Right?
Well done, Jana. Yep. I get it now. Where were you 5 years ago?
Struggling to learn Latin.
So notice below that we're asked to draw the given angles on a separate paper, right? And so here's where we're given the hint to use a protractor. And so we're going to look at drawing a 45-degree angle, a 90-degree angle, and a 180-degree angle. And although all of these are showing that initial side to be the horizontal moving counterclockwise, they're all positive degrees. If I had decided to swap this and start with my not horizontal, with my slanted or my vertical line, it would still be 45 degrees. So as I'm practicing those on a piece of paper. And the goal there is one is just to practice recognizing these angles, and 2 is just to practice using a protractor. So that's what that exercise is there for. And then notice here, we're just being prompted to simplify. And so we're shown a conversion from 60 degrees to radians. And so we are using the conversion factor of pi radians over 180 degrees. And so my 60 degrees is going to cancel with my 180 degrees, leaving me with 3. So 1 over 1, and I'm left with pi over 3 radians. And notice I'm just going to emphasize radians is not actually a unit. And so we're going to write this here frequently for students so they know that we're talking about radians. But when we are using them in calculations, a lot of times you'll see it written as just pi over 3 because we don't need to say that it's radians. It's not an actual unit. All right, so now let's take a look at coordinate plane, and 2 of the things that we're doing this week that I meant to point out and didn't. The 2 big ideas this week are, 1, we're talking about angles, right? When lines intersect, we define an angle, so we're going to be talking about angles. But the other thing that we're going to be talking about is what happens when 2 lines intersect, and what does that look like algebraically and geometrically. And so working on that. All right, so let's take a look. It says to sketch the open, and notice that we're saying not equals to is like our open circles, right? Or closed, that's our or equals to, meaning that it's included, the line is included, inequalities, and then shade the intersections. So last week we looked at just 1 line and the inequality. This week, we're going to look at where the inequalities when we have 2 lines. So we're given y is greater than 1. So notice that that is going to be a dashed line because it is open, it's not included. So that is this line here. And my other line would be y, and I'm just going to say equals to here just because that's our equivalent line is x plus 2. So that is this line here, and it's a solid line because it's an or equals. So now I want to look for where is my region both greater than 1. So everything that's up here is greater than 1, but I also want it to be less than x plus 2. So that would be below this line. So this region here is where I'm both above line 1 and below line 2. All right, notice if I came down here, I'm still below line 2, but not above line 1. If I came over here, I'm above line 1, but not below line 2. And so let's go ahead and look at the other one. So my lines are negative x plus 2. And so here's 2, my negative x. It's an or equal, so I'm going to use a straight solid line. My x is greater than 1 is not equal, so I'm going to use a dashed line. And so I want to be greater than this, so I need to be above this one and greater than this line. So this is the region that is greater than both. Any questions on that?
Yes. How did you know exactly how to slant your X line?
So my slope here, so this would have been coming from last week, right? And so if this is not right, it may not be familiar for a lot of your students yet. You can either go back to last week, or you may help them give them the line and then have them shade. That would be a way to tailor this if you're working together. But my slope here is -1 and my y-intercept is 2. So I know I have to go through this point 0, 2, and then if my slope is -1, if I go up on my y, I'm going to go back on my x. If I go down on my y, I'm going to go over on my x. So I could either look at it this way, or I could look at it this way, and then I'm going to plot another point and draw my line. So remember, you could always say, okay, what happens when x is 0? Well, y would be 2. Well, what happens when y is 0? Then x would be 2, right? And so I can I can always build a table of values as well to help me graph. So for students who are perhaps not ready to use slope and intercept, using that table of values is probably the easiest way for them.
And Chrissy also knew what to do because she's done so many problems. So it's just like reading complicated music on the piano, or in a piece of music and playing it on the piano. And one of the things that we focus on is you'll see these kind of equations over and over again. I don't use a big variety of equations, so they can start to get familiar with very basic ideas.
Quick question about the table that you mentioned. If they're
Yes.
not ready to utilize the slope equation, where is that?
So you can look on chart 9.2. We talk about picking out points. So especially with lines, right? Here, if I have my x, and then for example, this is y equals negative x plus 2, right? I can pick values of x, and I can say, okay, when x is 0, negative 0 plus 2 is 2. And I can pick any point. I could say x is 1, negative 1 plus 2 is 1. And so I see here I've got 2 points, and as long as I have 2 points, I can connect those 2 points and I can graph my line. A lot of the times that we'll say is to then use y equals 0 and solve for x. So when is y equal, if y is 0, then we would say, well, x has to be 2 to make y 0. And so, so that's, those are oftentimes the easiest values there, are those 2 zeros. Once we get to in next week, when we talk about power functions and so forth, we still tend to look at the value where x is 0. It becomes a little bit more complicated to think about when y is 0, just because it doesn't always work out as nicely. So that might be a case where I pick another point like x equals 1 to help me.
So Kirsty, I always do -1, 0, and +1 for my x, with the hopes that that negative will catch any weird things going on with the equation. And I know, of course, as they get more complicated, it's not, it doesn't, you can't use it for every function, but you kind of get, as you do more problems, you kind of get familiar with what kind of numbers to check. So since this is a number line, or since this is a quadrant, or a grid, I should say, with 2 quadrants, I know that I'm going to possibly have some negative values, so it's worth trying. Versus if I'm told everything has to be greater than x equal to 0, then I'm going to have more positive numbers I would try. So you just by doing these 16 equations over and over again, you start to get familiar with them.
So let's go ahead and just look at the bottom where we're asked to label the explementary angle, and notice we're labeling the measure. Explementary always tells me that we're adding, our angles add up to 360 degrees. So we see that 360 degrees and 0 degrees would be explementary. How about 90? What would be explementary to 90?
270.
270. How about 135?
45.
Okay, so remember 45 and another 180.
Oh, okay.
Because I've got to go all the way. Which would be our 225. And so what would be, what would be explementary to 225?
135.
135. All right. Okay. So just a reminder of, again, every week we want to end with remembering that it is okay to work backwards from our solutions, or to just get part of it, right? So maybe you use the solution to help your student with the line that they're struggling to graph, and then you let them shade it in, right? So those solutions are there as a resource. The inside back cover helps to extend that conversation or give you some ideas for your lesson 29 booklet. Don't forget, we've got games. That careful calculations page is a great review. It can be used as a quiz or a test for families that are looking for some calculation type of assessment. Those flashcards are going to continue to help us to read math and build our grammar. And then the companion is there for you when you're looking to go a little bit deeper and answer some of those questions. I just want to always reiterate that it is there for our parents to use as a resource. It's not expected that you're using that all the time. Our pilot families over and over said it was a great resource, but that first year especially, the booklets were enough. And so I really want everybody to be able to rest in that. And then obviously we're practicing our math concepts through the lesson pages. Don't forget, there's lots of opportunities for you to get support. The companion is 24/7 there for you. The forums, I'm not sure if Babs, Shauna ever sleep, because I know that they're always answering questions until late at night sometimes and early morning. And then obviously with one another, right? To talk about math with one another. So we've got our next 4 lessons there. Notice we're almost through the first semester as we go through October. And I'm just going to mention now that when we get to constructions, you may want to have some tools in order to work through that constructions booklet. So if you don't have a compass, a straight edge, or some pen and paper, those are some tools that you may want to go ahead and get on hand to practice that week. All right. And so we are finished on time, but as always, we will stay here and answer any questions that remain. So if you have questions, you can go ahead and speak up or raise your hand and we'll answer those.
Go ahead.
I was just going to make a quick comment because I haven't heard this said very often, but I think that you would agree with this. If you are working through the curriculum and you don't finish with a week, don't get bogged down trying to catch up all the time. Like I realized one of my students was like, no, I'm still on week 3 because I'm like, stay on the weeks that your community or family or whatever, like, right? Isn't that what you would say?
Absolutely, Jana. It's a great encouragement. That one of the things we didn't want people to feel like was that you had to camp on something. And we actually are going to be releasing a blog that that likens going through the math map to reading The Lion, the Witch, and the Wardrobe, right? And so if you think about reading The Lion, the Witch, and the Wardrobe with your students, if you who has read it before, and you know all the symbolism and you're really excited, right? If every time you get to something, you stopped, right? So you meet Mr. Tumnus and you're like, okay, so before you read on, I really want you to notice, did you notice the lamppost here? What do you notice about it? Like, do you understand it? Okay, well, now Mr. Tumnus, do you understand who he is? Now I want you to keep in mind, because you're going to see him again in a little bit. And right, we don't do that. Can you imagine reading The Lion, the Witch, and the Wardrobe if you stopped and just beat it to death every scene, right? We keep going because we want the kids to be into the story, because they're going to come back to Narnia over and over again. And we're going to be able to come back and talk about all of these different things that are so exciting about Narnia. Well, let's treat the math map kind of the same way, right? Don't get bogged down so that if your student's struggling, you just well, that's it. We are going to stay in the hard place. You never get to leave the hard place. We're going to stay here, right? Can you imagine how discouraging is that? So instead go, you know what? We did the best we could this week. And maybe when we get to a break week, we're going to come back and look at a couple of these pages. But let's go ahead and move on and see what next week has for us. That is, that is a great reminder, Jana. So
The thing is, Peter will say, you just gave us a good lesson though, and we can 10, I mean, not, no, what did we just finish, 9 or 10?
10.
10, right, okay, because week 9 is where we taught something people had questions about, and 10. So they're like, well, how can I do 10 if I didn't do 9 and learn that when I get to 10? Well, what I would do is say, okay, here's something I don't know. Let's go look at the solutions, or let's look at the chart. I wouldn't maybe even finish the problem. I would use it as a place where my brain does something rather than my hand. Right, there's always a way to move on.
Okay. Okay, so that actually was my question on some level. So because I was thinking when you said, oh, this comes from week 9, when we were talking about the slope intercept form, and then I thought, okay, I haven't done week 9 yet. So that actually does answer that question. But another point that I wanted to make is that I have like a green wax highlighter that I've started using, where I'll just go and I'll just highlight a whole section that I didn't understand or that I didn't quite get. And then I can just move on, just because my brain wants to know, to like, okay, where do I go back to when I do get to it? You know, when we're on, you know, a 5-week break, and I don't really have a 5-week break for my homeschool. So that's one thing that I think has helped me mentally check it off, because, you know, it's kind of like you're trying to hold on to it because you don't want to forget it, and then you can't hold on to it. So I thought I would say that. Shh, my kids decided to get loud right now. The other question I have is about, so the first one was about when you haven't finished, and the second one is about how you would answer. So last week I asked the question about one of my students really misses the success that he feels from calculating a whole lot of things. And the excellent response was like, how about we help him to tell him to make up some of his own problems, which I thought was great. Pass that on. But then we're contending with the fact of like, how do I know that the problems that he did are right as the parent who is correcting them? So can you help me have an answer to that? I mean, not that there's one answer, but just can you give me like kind of what kind of conversation you would have about that?
Sure. So one, as a parent, if I'm not confident in my calculations, right? So I'm not confident enough to sit and go, yeah, you got that right. Great job. Then the best way to do it really is to find a buddy, right? Find a friend who maybe is a stronger calculator, and say, okay, look, we're going to have you two do this together. Both of you are going to play this game where you're going to deal out cards, and we're going to add them together or subtract them or whatever it is that we're going to do. Now compare your answers. Are they the same? Then chances are you probably did it correctly, right? They may not have, but okay, they're different. So why don't we stop and take a look and see if one of you is right and the other one's wrong? And so that would be one way, right, is to turn it into a game, a 2-person game, where we work together to check each other's work.
And I think that that makes sense in the sense of like making sure that the kid knows that it's right. But I think I'm contending with the parent wanting to be able to check the answers and be able to say, yes, you're doing it right. And I don't know that there's an answer to that except through the calculation.
I mean, it's kind of like all the students who do N2K and get really good at it. They say the wrong answer all the time and nobody cares because it's a game. But the more they play it, the less often they make those mistakes. And we need to let them, always going for the right answer it's not bad. We want the right answer to things. But when you're learning something and it's new to you, it just takes time to get all of those. And so use the flashcard, use the national number knockout, and then use the games in quick flip arithmetic, which has exactly the same problem you're talking about. All those 3 examples, Nicole. You're not 100% sure that you're correct. That's okay. I mean, that's one of the things I learned when I went from, a big fish in a small pond called high school to the smallest fish in the biggest pond called aerospace engineering at the University of Michigan. And I'd gone from always being able to get the right answer to going to a place where I was being asked to think. And I could not think if I couldn't find the answer. And it took 2 years to break that habit. And so I'm trying to give your student a curriculum where there's some answers that are very easy to check. And there's some where you just go, I don't know what I'm doing. And then there's a few questions where there really isn't an answer. And that's why it says discuss. Trying to give them the freedom to explore and even be wrong.
And Nicole, I know you're trying to help those parents figure out how to assess what their student is doing, and maybe encourage them to change how they assess a little bit. So instead of trying to say, okay, I'm going to see if you did all of these calculations correctly, maybe have the student just explain their work for one calculation. And so assess their process instead of their answers. Because that's really what we want to get to. We've been trained. We have been trained, and when I say we, I mean all math educators. Okay. And I was a classroom math educator, so I can tell you this, that people in education, right, that they go, I like grading math because there's right answers and they're easy to grade because I can just go through and I can go, yes, they got the right answer. And I don't really have to like think, right? When you go to grade a paper, gosh, there's so many things you have to think through and you have to spend time on it. You have to write comments, right? So we like the fact that math is supposed to be easy to assess and grade because we're just checking answers. But the problem with that is that when we just check the calculations, a lot of the times we can have kids that are great calculators and they can follow the algorithm, right? They can follow the steps and they can calculate really well, but they don't really know what they're doing. And so as parents, we have not been trained, and educators in general have not been trained to really sit and help a student to self-assess or for us to assess their thinking that goes into the process, right? How did you do this? And so we kind of need to help parents and ourselves become more confident and more comfortable with when we ask a student to say, okay, what's 53 and 27, right? Well, 10 different kids might actually give you 10 different ways that they solve that problem. And so they may all get the right answer, but if all we're doing is checking the answer, we haven't checked their thinking. And you might discover some really cool things if you say to your student, well, how did you do that, right? Use words, don't look at your paper, just use words and tell me how you did that. That's going to help them move from the grammar stage to the rhetorical stage, right? That we're going to be helping them by breaking these conversations down, but it's also going to help us to assess, do they really know what they're doing? And it's uncomfortable because we have not been well equipped to do that. But I think that's where one of the breakthroughs is going to come through, is by changing how we assess.
Something else to think about is all the things I design in classical conversations. So we meet one day a week for half the year. So that in classical conversations, we're trying to do the hardest things together. When this year's over or it's Christmas time, go buy worksheets and let them do a whole bunch of them and use it. And all week, year long, use those alongside classical conversations. There's nothing wrong with being satisfied with playing the same piece of music over and over again, or doing the same problems over and over again for the same types. That we're supposed to be doing that. That's what makes it so that we're familiar, like Kirsty is. But those are all over the world. What isn't all over the world is a curriculum is trying to get you to think and see God. So that's going to be a frustration too.
Thank you very much.
Thanks, Nicole.
Christina.
Hi, yes, I don't know if we can go backward in a booklet. Is that allowed to ask a question from a previous? Okay.
Absolutely.
So I have two questions from booklet 8. That was the one that we just finished this week in our community. And if you could help me to understand, so I'm on page 9 and page 10. I'd like to start with page 10 where it says words, symbols, images, sketch the union of the opposite order intervals. I don't know why, but I I understood these previously, and this week's it seemed very difficult for me. I don't know, my brain must be slowing down or something. It's just the last one in that box that I'm struggling with, where it says X is less than 9. The union, I'm struggling maybe with how to even say this like numerical sentence. Union X is greater than 7 equals X is a set of, or is an element of reals. And when I did it, I felt really great about what I did. And then I looked at the answer, and what I did not match the answer. So I wanted maybe a little bit of clarification on how this works.
Sure. So, so this is the image that we have, right? So we have our number line, and we have 7 and we have 9, and we're given 2 intervals. We have X is less than 7 and we have X is greater than 9.
Right.
So if I
No,
was
is
to,
it the other way around?
yes.
Yeah, it was the other way around.
Yes.
Yeah.
I was gonna say
No,
this
X
isn't,
is less than 9. Yeah, that way. Yeah.
Yeah.
So those are my 2 intervals. And so as I look at these, right? So they're open circles at 7, and then drawing to the right, open circle at 9, drawing to the left. And we may be tempted to go, oh, there's an open circle, so it's missing. But because we're talking about the union, right? That value of 9 is included on this line here. This value of 7 is included on this line here. So notice I've got a line that goes the entire way. And that's where I would say that my answer is going to be that X can be any real number.
Okay.
And if we think about it, like if we were talking to our kids and we just wanted to think about this without actually like writing it down, right? Say, well, what number is either greater than 7 or less than 9, right? And then just pick some numbers, right? Well, a number that's greater than 7 is 8. Okay. Well, is that less than 9? Yep. Well, that fits. Well, what about 10? Well, 10 is greater than 7. Is it less than 9? No. But it has to be one or the other. Is it one or the other? Yep, it is. It was greater than 7. Well, let's try another one. Let's try one like 6. Well, is 6 greater than 7? No. But is it at least less than 9? Yes, it is. So is there any number that's not either greater than 7 or less than 9? Nope. Therefore, all of my numbers, right? So sometimes just speaking it through helps us with those.
No, that's extremely helpful, because I was just thinking, well, it's 8.
It went.
Yes, you were trying to make it an and.
Right. Yes, I was. Okay. And then my second question is on page 9. It's in the mapping box, and it's the multiply A times B for the very last example, which is 3 plus I, 2 plus 2I is an element of complex. And I understand, like how to combine to or FOIL. I don't know. That's how I learned it when I was a kid. So that's the word I'm going to use. But then I didn't understand how to get from there to the answer that was provided. In fact, I was actually totally stymied. This was the one that really, I just totally didn't understand, I guess.
Okay, so you can use FOIL. So just to clarify for everybody, it does not matter what method I use. Every single method is just a different arrangement of the distributive property.
Okay.
So I just want us to all be on the same page that however we arrange this, it's always going to be the distributive property. So I'm just going to go ahead for this case and use a vertical stack. So 2I times I would be 2I squared. 2I times 3 is 6I. Then 2 times I, I'm going to line up my like terms, is 2I, and 2 times 3 is 6. And so I end up with 6 plus 8I plus 2I squared. And I'm wondering if that's where you got to.
No, that's why I was confused, because that's not where I got to.
Okay.
I got to, oh yeah, okay, so I did get there. You're right. I got that far.
This is where we need to remember that I squared is the same as -1.
Okay.
So this is the same as -2. So now I can take my 6 and my -2 and combine like terms and get 4. And my answer is going to be 4 plus 8i.
Okay. That's what I was forgetting was those imaginary numbers are giving me some fits.
Yes.
Okay.
So one thing that we're doing as we go through is we're going back and putting in more and more steps for the
Right.
parents. So what seems obvious sometimes to me isn't obvious. And so we're listening. So thanks, Christina. And those problems with the unions and intersections, they're hard. You just really, they're brain teasers.
Yeah, that one was challenging only because I was thinking a little too concretely about it, and I was failing to recognize that it was an or rather than an and. So yeah, that's good. Okay, thanks, ladies. I appreciate it.
All right, Angela.
Thank you. I'm also an 8. My first question, I have a couple. If we could go back to the I2 page.
Okay.
Second section, solve one equation with one unknown value.
Okay.
Add or subtract. So first step, add or subtract to isolate the x term. So I don't actually see how the isolation is happening here. When I look at the chart, the blue chart, the same step is given, chart 8, page 2. On the right-hand side, add, subtract to isolate the term. When I compare these two problems, they're actually the same, except that in the I page, it didn't start with the problem before you went to adding 2 to both sides.
Right.
It's quite confusing to look at the +2 on both sides as the first step. I see it here in the chart that you need to add 2 to both sides, because now I see that's how you got 3. But I think it actually just came to me that that's what happened. That you used the same problem, but in the blue, you gave the original, and in the I page, you actually did the step without giving the original problem. Gosh, that was very confusing to me.
Yeah, that's what happened, was the original problem got lost there so that you didn't see where we started.
Oh my goodness. I didn't realize until I just said it out loud that they were actually the same problem. So that's helpful. I'm just going to write the chart 8, page 2 for original.
Percy, is that the page where I have that it's like a major errata? Is that where she's looking?
I'm not sure if that is.
Yeah, do you guys know to double check your errata sheets before you make yourself crazy?
Where I haven't even printed that out.
It's not on the errata.
It's not on the errata, okay. Yeah, I don't have the book. I can't see what she's looking at.
Okay, thank you. That makes so much more sense now. Okay, next question was on page 1 of lesson. No, it wasn't page 1.
Do you see how social math is by just talking out loud, just solving your own
so
problems?
much. I did already. I texted my AR, who's my social math buddy, but we couldn't figure out. She's like, "Oh, they're giving you baby steps." I said, "No, nothing has moved from one side to the other side, which is what we need to do to isolate the variable." Anyway, okay. 10. Intersected lines, page 1. Middle section, intersection of 2 lines. And it says compare, equal, not equal, M1, M2. And then all across the bottom, there's 3 different options that appear to be in the same box as the top section. I don't know what are we talking about here?
So
What are we
those are the
What page are
slopes.
you on again? What page?
Page 1, lesson 10.
So what you're doing there, so is yes, they are all connected. So if I have two parallel lines, you're going to compare the slopes of each line. And so if they're parallel, what's true about their slopes?
They're the same.
They're the same.
However, what happens in the next box?
So
Why is it
when I have,
negative? Go ahead.
yep. So when I have two perpendicular lines, there's a relationship between their slopes, and their slopes are going to be negative reciprocals of one another. And so the slope of 1 is going to be equal to -1 over M1, right? So those are going to be equal. And
Why
that
did you
should,
switch the order and put M2 first in that section, that second one?
it could have gone either way, but the reason, honestly, the reason why is because if you look on chart 10.1, you'll see here that I'm writing next to the slopes where I say one line, the slope of M1 is -1 over M2, and M2 is -1 over M1. So it's just expressing one line or the other. And so if you look there, you would have seen that relationship to know that they're equal.
Chart 10.1. Okay. Okay.
And then the same, right? When I have coincident lines, their slope is going to be the same. So that's what you're doing in those boxes there.
Okay. I am, I believe I'm done. Thank you so much. Oh,
You're
no,
welcome.
I'm sorry. One more. You said it, but I was looking at the chart and I couldn't find where you said the table is explained to get your, like, your testing for your X and your Y.
Sure.
From
It's
9.
chart 9.2.
Okay.
Down at the bottom where it says graphing linear equations. On the
Okay.
left-hand side, it says
I
use a
see it.
table of values.
So you still have to use slope for that though, correct?
No, well, you're using slope, but only in the case of that's the equation, right? So if y equals mx plus b, so let's say I had y, here's my x. If I said, here's the equation of my line, right? I'm only using slope in the terms of solving within this equation. So when x is 0, right, 4 times 0 minus 3 is -3. When x is 1, 4 times 1 is 4 minus 3 is 1. And I could keep doing this. I could use -1. -1 times 4 is -4 minus 3 is -7. That's all I'm doing.
Could
is
you
I'm
do
taking
something really silly and go to page 2 and remember how someone said, how did you know how to draw that line? And you said, well, I could have used slope, but I also could have used the table, right?
Sure. So in that case, I had x, and I think we were doing -x plus 2.
Right.
Right? This is my y. So when x is 0, this is 2. If x
Okay.
was -1, I'd have -1, which would be 1 plus 2 is 3, right?
Why
If it
is
was
that
1,
your y?
because that's what, so it tells, when it says y is greater than or equal to -x plus 2, I'm
Okay.
always going to look first at the related line, right? So that line is what I'm going to be graphing, and then shading left or right of that, or up or down from that, depending on my inequality. But I'm always going to start by graphing what the related line is.
So for line 4, all I see is x is greater than 1. I don't see anything that has a y in it.
Right. So that's in that case, right? So here's my case, right? So x, let's look at x equals 1. And so what this is telling me is that x is 1, 1, 1, and y could be 0, 43, -196. It doesn't
Okay.
matter what
There's
y
no
is.
calculation. I see.
There's no
Okay.
calculation, and x is just always 1.
Okay. And that's why it's a straight line.
That's why it's a straight line. Yep.
Okay. And so if it were a horizontal line, it would be y equals
Yes.
1 or something like that.
Yep. You got it.
Okay. Thank you.
You're welcome.
You guys make me happy.
Well, great job thinking through math today, everybody. And we'll look forward to seeing you next week when we look at all of our power functions. So it'll be a fun week.
Thank you.